Hi everyone, and welcome to a brand new Tech Tip series here at Mr. Carlson's lab. If you want to grow your electronic smarts, definitely subscribe and hang around. I'll have many more Tech Tips videos coming in the near future involving modern and antique electronics alike, so there's something here for everyone. In this video, I'll explain why you add this component, which is a diode, across the coil of a relay. It's a very important part to add. I'll explain why. I'll show you why. You'll actually get to see what happens if you don't add this component. So let's get started. I have got so much great information to share with you in this video. This will also help you understand how boost converters work, boost power supplies, all sorts of great stuff will be demonstrated in this video. Something as simple as a diode in a relay can explain so much about electronics. And again, this is the kind of stuff I teach in my Patreon electronics course. I try to convey as much information and cram as much information into a video as I can in order to help you learn about electronics. So in this video, I'll show you exactly why a diode is needed across the coil of a relay. In many applications on circuit boards, you'll see this little red glass diode at one end of the relay, or in some cases, if they're much larger relays, you'll see a diode like this. Usually they're very close to the coil end of the relay. So I'll demonstrate here why this is needed, and of course, as I'm doing this, you're going to start to understand a lot more about inductors as well. So relays, inductors, boost supplies, all of this is going to become very clear, all because I started talking about a bunch of diodes. So anyways, let's do this. So I'll apply some current to the coil of this relay and you'll hear it click normally. All right, everything seems to be fine, right? No problems, right? It's clicking away. Why would I need a diode? Okay, so I'll grab one with a diode across the coil. Okay, so I'll attach this here to this side. I need to be very careful, of course, which polarity I attach this, because this diode here will short my power supply otherwise. Okay, so here we go. Same deal, right? You can hear it clicking, right? Nothing different, right, between this and that. So what's the point of adding this component? Well, here is the trick, and this is why you add this component, and this is very important in automotive application as well. So if you're installing relays to control fans in your car or fog lights, or anytime you install a relay, you should have a diode across the coil, even if it's just a switch turning it on and off. I'll explain why. So here I have a neon bulb across the coil. Neon bulbs strike usually between about 70 and 90, sometimes depending on the neon bulb and the actual electrode spacing, they can strike up to 120, 130 volts. But when they do strike and they start to glow, they go from basically a high resistance or high impedance state to a low impedance or low resistance state. So they act as a clamp. That's why you see neon bulbs and gas discharge bulbs used as lightning arresters on antennas, because when they don't glow, they look like an open connection, but the moment they glow, they clamp. They're very much kind of like a crude Zener diode. You can actually use neon bulbs as regulators as well. I'll talk more about that here in the very near future. Again, a good reason to stay tuned. I've got so much great information to share with everyone here. Okay, so you can see this little neon bulb. I'll try to make this as clear as possible. So I'll attach the positive of my power supply. So these are a 12 volt coil. So it's a 12 volt, across this and this right here. So basically a 12 volt relay. Okay, so keep an eye on this. Hopefully you can see that. I want to kind of cover the light. Okay, so I'll touch this. You see that flash? So now it actually doesn't flash when I first touch it. It's just because you can call that bounce. It's almost like switch bounce when I'm touching this. So if you watch it, you see how it didn't flash there, but now it will flash, no flash, and then flash. Well, what's happening here is when I'm applying 12 volts to the coil inside this relay, like so, it's magnetizing the actual relay, and then when I remove the 12 volts, the magnetic core collapses. So basically the magnetic field, I should say, collapses. And what that does is that creates a high voltage pulse that is reverse to this. How do you know it's reverse? Well, what happens in a neon bulb is the cathode will glow if you put DC across a neon bulb. So you can see we have 2 poles inside this little neon bulb. If you look at a neon bulb in, say, a night lamp that's powered by AC, okay, you'll notice both poles inside the neon bulb will glow orange. That's because AC is going back and forth. It's switching polarity. So it's basically lighting one pole on half of the cycle and then lighting the other pole on the other half of the cycle. So it's switching back and forth. So it's actually moving back and forth very, very fast. When you apply DC to a little neon bulb like this, only one pole will glow and it'll actually indicate the polarity. Again, the negative or the cathode pole will glow. So now, if this is the positive from the power supply and this is the negative from my power supply. So I'll touch the negative on here and watch very closely in the neon bulb which pole glows. So here we go. Now watch. Did you see that? This pole here is glowing. And again, the reason that you're seeing it sometimes flash when I touch the wire and when I remove it is because of a thing known as switch bounce, basically. So if I make a perfect connection when I touch this, no bounce, and I remove this, is when you're actually seeing it. Switch bounce is basically like when I'm touching this wire here, when I'm touching the negative to this wire here, switch bounce is like it's making connection and not and making connection and not very quickly because the connection isn't very good between this and that, right? Again, that's known as switch bounce in electronics. They have switch debouncers. You can build them with all sorts of different types of components, and sometimes even putting a capacitor across a switch works very well as a switch debouncer. But anyways, back to this. Again, trying to get as much info in here for you as possible. So you can see that this upper pole is the one that's flashing. Well, that's the negative side. Well, if you notice here, this is the positive side from my power supply, and this is the negative side. Why, when I remove this, does this become negative and this is positive? Well, what happens is when the actual magnetic field collapses in here, it creates a pulse that's reverse polarity to what I'm applying on this, all right? So this is 12 volts, right? And now I get a reverse polarity, high voltage spike coming out of that coil. Why does that happen? Well, it's the same thing that happens in a car ignition system with breaker points and things like that. When the breaker points are closed, what it's doing is it's magnetizing basically that core inside the ignition coil. And then when the breaker points open is when you get the spark at the spark plug. So it's not actually when the points close, but it's when the points open is when you get the spark. The same as this. You'll see the flash when I lift off. Now, here's the thing. With this out of the way here, I have a transistor doing the switching, all right, a little 2N3904 on here. So what I'll do is I'll attach the power supply to this, just like so. So now this transistor is going to be the switch that's turning this on and off, okay? So this is a little 2N3904, okay? Now notice that there's no protection diode on this at all right now, okay? So I'll grab, this is just a little button cell power supply that I can turn on and off. So I turn a bunch of button cells on to turn the transistor on, right? So this is a 120 ohm resistor in line with the base to limit the current, because remember we have junction in here and we definitely don't want to apply any type of current to that junction, because at 0.6 of a volt, it kind of gets a little bit unhappy if there's no current limiting, right? That's why you have a resistor in line with the base of a transistor to limit the current, right? So what I'll do is I'll attach the negative again to the negative. So I have two negatives bridged here, right? This is to the emitter of the transistor. So just like on the schematic, you'll see the emitter of the transistor goes to ground. This here will go here, Okay, now I can press this little button. I'll back this off so you can see this. I'll press this little button here and it's going to turn the relay on. You'll hear it click. Hear it clicking on and off? So this is acting as a switch right now. I'm using a very low voltage here, just a button cell or two inside this little box. And this little switch is just telling this transistor to turn this relay on and off. All right, so I'll remove this and press the button. You can hear the difference. Right, nothing's happening. It's just me pressing the button. And then you can see again here. Okay, now you'll notice that there's no diode across there and nothing seems to be happening, right? It's still switching fine. Everything is okay, right? There's no diode and the transistor's doing it just fine. A little, weak, 2N3904, teeny little transistor, right? No problems, right? So why do we even need a diode? Everything seems to be just fine. Well, let's move up to the next display. Okay, so now I've got a neon bulb across this relay with a little 2N3904. Now this is where it gets tricky. So I'll move this over here and I'll do the switching the exact same way, but now we have a neon bulb as an indicator. Okay, you're probably thinking, I know what's going to happen. Well, I might trick you. You can tell me in the comments below if I tricked you. Okay, so I'll zoom on into this. You can see the little 2N3904 and a neon bulb here. I'll try and bend the neon bulb so you can see that just a little bit better. See the little poles in there? Okay. So I'll squeeze the switch here and watch what happens. Well, look, the relay's clicking. You can hear the relay clicking quite loudly. But there's no flash in the neon bulb. So again, why do we need the diode, right? Right? All right. So now here's where it gets tricky. Now, instead of using a 2N3904, I'll use a different transistor with a much higher breakdown. Okay? So this is an MPSA42 transistor. It has a much higher breakdown on it. So we'll do the same thing with this little neon bulb. We'll bend the neon bulb so you can see that a little bit better as well. Okay. I'll apply this to here. Put this on here. Like so. Again, current limiting. Now watch what happens. That's flashing with this transistor, but it wasn't flashing with this other transistor here, the one that I just dropped. It wasn't flashing with the 2N3904, but it is flashing with the MPSA42. Well, what's going on here? Well, this little transistor is actually breaking down inside before the actual neon bulb gets to strike. So this little transistor is taking that spike. It's taking that basically inductive kick that this relay is giving, and the transistor itself is absorbing that issue. Well, what will end up happening after a while if this relay is used in service? Well, this little transistor is going to become a jumper. So it transforms itself from a switch to a jumper. That's what transistors do. They turn from three-legged devices into two-legged jumpers. And it'll eventually destroy this transistor. Again, you can see, let's turn the lamp down here maybe a little bit. Again, you can see with a much higher breakdown, it's allowing this to actually flash because this is basically turning off and allowing a much higher voltage to develop across those two terminals right there. So that inductive kick that the relay is creating still might actually be going after this transistor, right? But at a much higher level, a higher level that's allowing this neon bulb to still strike. So what's happening here is a relay, when you actually remove the current from one side, we see that the cathode, or the negative side, the negative pole in the bulb, flashes. This is clamping the voltage that is, or the current and voltage is being created across this relay. It's clamping it at usually about, well, you could say, between 60 and maybe 100 volts or something like that. It'll clamp it there. Again, the current is very low, right? So it's basically just that little inductive kick that's being created. But that low current inductive kick is what destroys transistors, and that's the reason that a diode like this is put across this. So basically what's happening is, how if you put positive here and negative here, the relay clicks, right? So I'll just grab this again and display that. So we have positive here, and you can see the relay is clicking, right? What's happening is because the diode right now is not turned on when we do this, right? Because the diode is technically, to our power supply, it's actually backwards, all right? So it's not turning on when I apply current to the relay. So the power supply is supplying a much higher current like this at 12 volts than the inductive spike creates the other way around. So now remember, when I'm removing this, like so, that inductive spike is reverse polarity. So now this is positive. Well, what happens to that inductive spike? The diode takes it and shorts it to the other side. Because this is now positive, it travels through the diode this way and shorts like this. So basically the diode's invisible when current is applied to the coil, but the diode becomes very seen to that inductive spike, and it takes that inductive spike and shorts it out. Now, in an automotive application, here's something that a lot of people don't realize about relays, and this is the kind of stuff that isn't talked about. And again, this is the kind of stuff I teach in my electronics course, the stuff that really isn't so discussed, okay? Here we go. In an automotive application, when you buy a relay and say you're going to hook just to a standard switch to the coil, okay? So you're just turning it on and off with a standard switch. If you don't have a diode across the coil, even if you're turning it on and off by a switch, when you open the switch, depending on the actual coil in the relay, it can create such a high voltage spike that it will short the windings inside the relay after a bunch of times. It breaks down the little copper wire varnish inside, and it'll actually short the coil. So many times, if you've worked with relays in the past, you'll find a relay that actually has an open coil that has, had DC applied to it. And you're thinking to yourself, the coil looks fine. It's not burnt at all. Why is that coil faulty? Well, because what happens is when the wire inside breaks down, because it has that very thin varnish on it, it will short, right? So that'll short on the inductive kick cycle. When you turn the switch back on to actually apply current to the coil to energize the relay, now that the inductive kick has shorted that coil, when you apply current to it, it burns the wire open on the coil somewhere inside. Depending on how tightly wound that bobbin is, and of course, how well the actual coil wires are varnished inside, will dictate if it breaks down or not. So for many of you that have had that mystery, why did the coil actually open inside the relay? If you're going to install a relay on a switch to control fans, or if you're going to install it to, say, control fog lights, or whatever you're going to be, using the actual relay to control, always make sure that you put a diode, again in reverse, so that you're obviously not shorting your supply out. So the line side of the diode goes to the positive, right? Make sure that you have a diode in there, and it'll save the coil so you don't get that high voltage pulse when you open the switch, right? And again, this poor little 2N3904 here was absorbing that pulse right? This was actually taking that little high voltage pulse, and of course, because this was breaking down inside, much lower than the striking voltage of the neon bulb here, right? This was absorbing that, you know, the actual punishment from that little inductive spike. If you would like to increase your electronics knowledge to a much higher level and gain access to many of my personal electronic inventions, creations, and designs, you would definitely want to be in my electronics course on Patreon. I have over 220 videos there at this point for you to learn from. Projects for you to build, both solid state and antique alike. So whether you like to build solid state surface mount projects, or whether you like to build vacuum tube point-to-point projects, it's all there for you to learn from. Again, there's something there for everyone. If you'd like to check this out, I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comments section. So if you click on that link, it'll take you right there and you can check it out. All right, until next time, take care. Bye for now.